Okay, we're recording now. So, the last concept for this topic that I want to talk about is electronegativity. Okay? So, if you can write that word down, it is an important word, and it forms the basis of why the periodic table behaves the way it does, why certain atoms behave the way they do, and drives the force of a reaction between two elements.
Hello, Cassie.
They're saying hi, Cassie, if you're watching. What did Trump do today, Cassie? All right, no. Let's use this for what it's meant to be used for. All right, the electronegativity of an atom, okay, is the attracting power that the nucleus has for its own outer electrons and those of its neighbors. So in the nucleus, you've got those protons, those positive protons, which exhibit an electrical force. And this is what's keeping the electrons in place, but it's also attracting others. So the electronegativity is the attracting power, how powerfully that atom can hold on to its electrons. And some hold on to them better than others, as we'll learn. Basically, how badly it wants electrons. Right? How badly does it want it? So some of these are going to be addicts, and some will only be casual electron grabbers. I hope that metaphor landed. Now, I mentioned a couple lessons earlier the idea of Coulomb's law. Coulomb was a French physicist who worked with electricity and electrostatic forces. And basically, it states that an atom's electronegativity is determined by Coulomb's law. The size of the force is proportional to the size of the charges and inversely proportional to the square of the distance between them. What does that mean? Well, basically, if you extend the radius, okay, every time you extend the radius of that orbital, or the distance between the electron and the nucleus, that force diminishes twofold every single time, okay? So if it's inversely proportional, the greater the distance, the far less force you're going to have. If it's proportional to the size of the charge in the nucleus, that means the more protons you have in the nucleus, the more force it's going to have. And they play in balance, okay? So the attraction of the nucleus and the distance the electrons are away from them. Now remembering opposites attract, of course. Positive attracts negative. It's a basic physical law. Okay. I'm going to move on. Again, this is all recorded. So if I was to put that law in symbols, and I don't expect you to reproduce it, I just expect you to mention Coulomb's law at some point. But just to give you an idea, you'll probably come across this in physics anyway. The force, okay, equals the two charges times together divided by the distance squared. All right? And when we look at the charges, Q1 is the charge of an electron, and Q2 is what we call the core charge, the nucleus charge, which is the number of protons an outer electron sees and the number of protons minus the number of inner shell electrons. We'll look at the core charge in depth in a minute, but just to give you the physical representation of that law. Okay? Force. K is a constant. K depends on if it's in air, it's going to have a different force as to whether it's in water. All right? In general, we just assume that it's in space, in a vacuum. So the constant doesn't affect it too much. But if you have two charges in water, it takes the force weakens because you're passing through a different kind of medium. All right? How many of you are doing physics? Awesome. So you'll come across this at some point. Joel, no. Thank you. All right. So, core charge. In order to calculate how much charge that nucleus has, how much power it has, we work out the atomic number, because that's how many protons it's got. So if we look at magnesium, its atomic number is 12, it's got 12 protons. And we also work out the electron configuration, because if you've got all these negative guys in the way, it's going to diminish that force as well, because these guys are shielding the electrons on the outside. So the core charge ends up being 12, take those inner shell electrons, we've got 2 and 8, so 12 take 10. Lo and behold, the charge overall, the core charge is plus 2. That's great because it happens to be in group 2 of the periodic table. All right? And it happens to be the number of electrons it can take from something else. So that's the reason why it's peeling electrons off. It's because it's got that imbalance and it's holding on to those electrons. With chlorine, okay, you've got an electron configuration of 2, 8, 7. Those inner shells add up to 10. The outer shell has 7 in them. And looky here, 17 take 10 is plus 7. It's in group 7. All right, so the actual groups they're in is determined by the core charge. It's also determined by the electrons they can take. And we see that that means that this guy has a lot more potential to take electrons than magnesium. Okay, magnesium's only got a core charge of plus 2. Chlorine's only got a core charge of plus 7. And I know that too because metals always give up their electrons. And non-metals always take them. And the reason why they're taking them is they've got a bigger core charge. All right, we learned about ions and electrons being transferred from a metal to a non-metal. The reason why is that force of electronegativity, the ability to take electrons and hold them. So if you look on the periodic table, fluorine, chlorine, oxygen, nitrogen are extremely high in electronegativity. They're down that far end. They've also got smaller radiuses. There's not a lot of shells there, so the distance is smaller. This gives them a power to hold on to electrons quite well. If I go down to francium, all right, francium's got a core charge of plus 1. So already it's not holding on to the electrons quite well. But if you look down here, it's got so many shells. It's got 1, 2, 3, 4, 5, 6, 7. 7 shells going out. Huge distance from the nucleus, relatively speaking. So that means it's really hard for francium to hold on to its outer shell electrons. So those electrons really want to just get out of there, which makes it the most reactive element. Okay? The reason why it's so reactive is because it can't hold on to its electrons so much. And then those electrons go, and then it bonds with something. And it happens so rapidly that if you put, a centimeter of francium into a bathtub, you've got yourself a sizable weapon. Okay? A bomb. A bathtub full of water, right? Similar to what we do with sodium. Sodium has less electronegativity, doesn't hold on to its electrons quite well, so those electrons bounce off and they react. Boom.
So what would typically be the difference between sodium?
Well, the difference is the distance. Remember, francium's got 7 shells, sodium's got 3.
But like the explosion from like a little bit of sodium.
Francium, the explosive radius would be, you wouldn't want to be standing around, basically. Yeah, I can't get that. If I have that, I go into a special file.
You wasted all that trivia would be very
I've got new sodium. I've got some new stuff.
Better stuff?
It kind of was. I waited, yeah. I put my order in. I was like, yes. Awesome.
Do it. That's
Now, there is a group of elements that have no core charge at all because they're quite stable. And they are our group 8s. Neon holds onto its own electrons with a core charge of +8, but it can't hold any more electrons because the shells are filled. So that's it. It's done. Okay? If it was to form bonds, the electron must go into the next shell where the core charge would then be 0. All right? Because 8 take those electrons, you have a core charge of 0. It can't hold on to them. Noble gases. Right? That's the theory as to why that happens. We've heard of noble gases. They don't react, or inert gases. That's why. Okay? Because if you actually put another electron on the outside, their core charge would go down to 0. It'd be impossible for them to hold on to anything. So they're stable. Don't do nothing. So all group 8 elements, the noble gases, do not form any compounds under normal conditions. I say that, okay, because chemistry has exceptions to every rule. It's more magic than science sometimes. There are ways of manipulating noble gases to hold on to compounds. But I won't go into that because that's quantum sort of chemistry. But yeah, just understand that they have no electronegativity values. They have no power to hold electrons. A guy called Linus Pauling, of all people, assigned numerical values to represent the electronegativity of the various elements. The larger the number, the more strongly the nucleus holds onto its own electrons and tries to attract nearby ones. So there is a scale of electronegativity, which is informed by the core charge. Fluorine is the most electronegative element, and we rate that as a 4 on the Pauling scale. All right, it's kind of like a seismic scale or a pH scale. It just says that it's the most electronegative. And the reason why we know that is because if we actually did the calculations, we see where fluorine is. Okay? It doesn't have a lot of shells, so its electrons are close by. It's got a very high core charge of +7. So that means fluorine can just take electrons pretty easily from something else real quick. All right? It's got a higher power to attract. That's why it's there. And oxygen and chlorine is sort of getting into the second most. Okay? Good. So if we look, oxygen is the second most with 3.5, and chlorine third at 3.0 electronegativity. That's why oxygen reacts with everything quite easily. If you light a match on anything, oxygen's going to get right in there. Take those electrons away for itself. Okay? And chlorine reacts with most things too. Takes electrons away, such as sodium chloride. The chlorine will just take that one electron from sodium to form those ions. So, in terms of trends and your periodic table, electronegativity values increase as you go across the period and as you go down a group. Decreases, sorry, I should say, as you go down a group. So increases as you go across a period, decreases down the group. So you have this shift on an angle. And for that reason, nonmetals have high electronegativity. They only need 1 or 2 or 3 more electrons to fill their shells. They've got a high core charge. They're going to take them. And metals have low electronegativity, as I said, okay? Because it is easier for them to lose 1 or 2 or 3 electrons than it is to gain them in order to achieve a full outer shell. So that's electronegativity. Now, why don't we just demonstrate? Where is something I could use? Just take this pencil here. Can I just get a volunteer? Just to try and illustrate what I mean. Coop, can you just hold that loosely in your hand, please? Coop is a metal. I'm a non-metal, extreme power, can hold on to electrons, really like them, really attracted to them. I can grab it like that. Coop's now a charged metal ion. I'm a negatively charged non-metal ion. All right? Now, if we were both non-metals but still had this attractive force, what's going to happen? All right? So, just to show the folks here, we're pulling back and forward because we have equal electronegativity. We formed a covalent bond rather than an ionic bond. Okay? So now we're forming a molecule. We're going to exist as a pair like oxygen does. Because they both have the same electronegativity, they hold on evenly to their electron. Does that make sense?
Yes.
Yep, but if it's a metal, say if Coop was sodium, I could just yank that and it's mine. Now, when you get two metals together, it's a bit different. So what happens is, you have an electron, I've got an electron, and I'm like, oh, I kind of want yours, and you don't really want mine, and you don't really want that one now, and you take that, and then you can take that one, and I'll give you a couple more electrons there, and then you take that for a bit, but then I'm going to take that. That's how metals work, okay? They got this constant flow of electrons, and that's why they conduct electricity, okay? We'll look more into that in bonding, but that's just a way to remember that the different kinds of electronegativity. Because metals don't have it, they're quite loose with their electrons. You know, they sleep with everyone? No. Sorry, Coop. But yeah, just an idea of strength. Yeah, all right. I'll stop it there. So the core charge, the question is what determines core charge again? All that is I'll go back. It's the number of protons, over here. It's the number of protons, okay, minus the number of inner shell electrons. So if you look at chlorine, it ends up having +7 core charge when you compare it to sodium, which has a +1 core charge. Yes, but I said inner shell electrons. Not quite. What do you mean? Well, let's look at the formula.
Yeah, that's what I thought.
Yeah, like there's two electrons on the outside of the magnesium, and the core charge is +2. Which could literally
Yeah, you could.
amount of electrons.
Yeah, sorry. Now I know what you're saying. Yes, of course. All right, the periodic table works both ways. It tells you core charge and the amount of electrons in the outer shell.
And that charge is because it wants to get...
But the reason why it's holding onto those electrons is because of the core charge. All right, so it's all the patterns and they all blend together. But if you know those patterns, you can really make informed decisions of what to use and where. Okay, so it's kind of just like jigsaw pieces, but now you know how they all fit. Go back a slide? Sure. This stuff I don't want to focus on because this is physics, but yeah. I'll stop the recording.